Yes, so my name is Dang, as Mark has said. My website is Dang.it, that I have very graciously bought from the Italian government. I am Italian, but yes, funny joke. Anyway, so get with the program. So tonight, most astronomy talk usually goes into very fantastical details about black holes, magnetars, neutron stars, amazing things that you won't see. Tonight, I will bring it back to some very basics. I will first talk about what you might see in the sky, right? Like even tonight, when you have the observation session later. And then I will talk about one thing that you might see, which are comets. And we'll then transition into how do we learn about comets and what might happen to comets in the far future, which is my thesis research. Unfortunately, that won't be in too much detail, so I welcome any questions afterward about that. Yep. So hopefully by the end of this talk, you will know what on earth is going on here, or I guess not on earth. So what I work on is called planetary dynamics, which I like to say is the oldest field of Western theoretical astrophysics, or just theoretical physics in general. People have seen things on the sky for thousands of years, and for just as long, we have wondered why things move, how they move. So, and this study has been done, and I mean, the ancient civilizations like the Mayans, the Mesoamerican civilizations, the ancient Greeks, ancient Chinese, they all had ways to predict motions of stars and planets and things in the sky. So this is certainly a long tradition, and the biggest advance really in making progress here came in the 15th, 16th, 17th century with Copernicus, Galileo, and Newton with laws of dynamics. So I see dynamics a lot. So what is dynamics? Dynamics in general in physics is just how things move. So when engineers say they do dynamics, it's how buildings move, or hopefully don't move. And planetary just refers to planetary systems. So things that would live in a planetary system would be comets, asteroids, these are what we refer as small bodies, and then planets, which are bigger bodies, like the Earth, or Jupiter, which is a lot bigger than the Earth, and the star, right? Because planets, comets, and asteroids revolve around a central star usually. So before I get into any of that, as I said earlier, we have seen the sky for thousands of years. So what might you see at night, tonight, for example? And an important question usually to ask any physicist is the time scale. How long do you see these things move? It's turned out to be a very informative question because how fast things move, how long they move, can actually tell you why they move. So let's do an example. So if you look up at the sky tonight, I hope you can see this. There's some stars there. This is actually probably a pretty good view of the Toronto night sky. You won't see much, just a few dotted stars. And if you lay on your back for several hours and you look at the sky, you should see things move in a roughly that kind of motion, kind of circular-ish motion. And if this video is faster, yep. And if you track the motion of the stars at night, they make these concentric circles in the center. Does anyone have a guess on how long this motion is? How long does it take for you to notice this kind of motion? 24 hours? Yeah, I heard 24 hours. Actually, it's more like 1, 2. You can just sit back and you literally see the star. So this motion is on the time scale of several hours. What else is several hours on the sky? Right? You see the sun move on the time scale of several hours, right? In the summer, it's a lot more several hours. In the winter, not many several hours. And same with the moon, right? So is there any connection between this motion and the motion of the sun? And it turns out the answer is just yes. Both are just due to the fact that we're living on this rotating bodies, right? We don't see it, but it is rotating. And that rotation caused the day and night cycle. And the stars are all in the background. They're not really moving. They kind of do, but I'll talk about that later. They don't really move. So this motion that you see, this circular motion and the circular motion of the Earth are actually just the same cause, right? We're on this ball that's spinning, so we're also spinning, so we see the sky spinning. And the one point that doesn't spin, the point right in the middle, is the point where the North Pole points toward in the sky. That point stays constant. That's called the North Celestial Pole. So if you get stuck somewhere and you want to find north at night and you don't have a compass for some reason, one way is to identify that point where all the stars revolve around. And hopefully you're not in the southern hemisphere, because if you're in the southern hemisphere, that is the southern celestial pole. So if you're at the equator, you just take a picture, take a picture of the equator, you'll see this kind of funky thing. On this side, this is the north celestial pole. On that side, that is the southern celestial pole. So if you are on the southern hemisphere, if you follow that, you will go to Antarctica. On this side, you go to the Arctic. So I guess make sure you be careful which part of the Earth you're in. And just to really make this clear, people take pictures of the sky, but they keep the sky constant. And when you do that, you see the ground moving. And this is actually the rotation of the Earth. So you can't see the rotation of the Earth itself. It's a really cool video. I really like that video. So of course, this is a practical talk. So how can you take a picture like this? Well, you can see something like this just in Toronto, look up at night, you see the stars moving. If you want to take a picture like this, just take a few hundreds every hour, stack them together. You can Google something called astro stacking software or something, and you can make something like that. It's actually very easy to do. That's something that we give first year students here as one of the first assignments to do. So it's something you can all definitely do. Okay, does anyone know what this is? Right, exactly. This is the Milky Way. Or explicitly, this is looking toward the center of the Milky Way. You see that there are dark structures and reddish structures. The reddish area are where a lot of gases, star formation, funky, fun things happen. The dark spot is where there's a lot of dust. So the dust blocks the light from coming toward us, and we can't really see through that in the optical, in the visible wavelengths. So I took this picture of the Milky Way in the summer, right up close to the summer solstice. You take the same picture 6 months later, it's gone. Like it's the exact same technique. I didn't like take a worse picture with a worse camera. Yeah, there are some clouds, but like it's not a big deal. But what happened? Why is the Milky Way gone? So the time scale, as I mentioned, is several months, right? From June to December, so that's half a year. So what is it going on the time scale of half a year? Well, the Earth, right? The Earth moves around the sun in 1 year, so half a year is on the same time scale as the Earth moving around the sun. So why don't you see the Milky Way in the winter and you do see it in the summer? Well, the reason is quite simple, is that during the winter, at night, you are looking out of the Milky Way. So during the day, the Milky Way is over your head, but the sun is there, so you can't see it because the sun is really bright. So in the winter months, you cannot see the center of the Milky Way because you're looking out of the Milky Way. During the summer, the reverse happens. At night, you are looking toward the center of the Milky Way, so now you can see the Milky Way itself. Same picture, same thing. I don't know why I put this in. So how do you get a picture like this? This is always the biggest question people ask. Did I invest millions of dollars into telescopes? And the answer is no. First you find a really dark sky. So I use this website, Light Pollution Map. This picture was taken right here. See, it's less light polluted. You cannot take this picture in Toronto because the light pollution would just obscure all the stars. And of course, you have to make sure the weather is good, because if it's cloudy, you can't take this picture either. And you just take a camera, point it up. You don't need a telescope, actually. You want something wide, like a wide angle lens, so you capture the entire sky. And make sure you go in the summer months. And that's it. Very easy. So everything we have talked about so far, every motion that we have talked so far, the motion of the Milky Way in the sky, the motion of the stars over one night, they're all due to the Earth's motion, right? It's the Earth rotation and the Earth motion around the sun. And the big question is, actually, before I go to the big question, this has been noticed by people for thousands of years. This quote by Copernicus say that quite explicitly. He said that the motion of the Earth alone, therefore, suffices to explain so many apparent inequalities in the heavens. Inequalities just mean things that move. And this is in 1543. This is, as I say, this is a pretty old field of research. So before I move on, I say that stars, only move because of the Earth rotation. They do actually move by themselves too, right? The sun travels around the Milky Way. Every stars move around the Milky Way. There are stars that move out of the Milky Way. A lot of things happen with stars, but they move a lot slower on the sky. And that really is not very noticeable over the course of months and hours. If you have a telescope, that's probably noticed over a course of several years or tens of years. If you don't have a telescope, it's noticed over the course of thousands of years. So it's really, really, really slow from the point of view of Earth. So how about things that actually move other than stars? So we are in 2024. We have passed the Copernican revolution. We know that the sun is at the center of the solar system. And there are planets that move around the sun, right? So we know that there are things that move around the sun, and a lot of things move around the sun, not just the planets, but also comets and asteroids, like I have said. So this is the motion of the planet Mars, which is our nearest neighbor, within the next year, actually, from August 2024 to July 2025. And you can see that it makes this motion, right? It's a little weird, funky loop, which I will explain later. But you can see that it takes about a year for this motion to happen. So in fact, if you look at other planets, this motion takes on the order of timescale of years. Right? So why is this? Why do planets move, one, in such weird fashion? Two, why does it make a loop? And three, why does it move like pretty comparable to the Earth? Right? By the way, the word planets just mean one with stars because people see this, right? Like no other stars make loopy loop like this, but this one really does loop. So it's an important thing to discuss. So this is called retrograde motion. And really the only model that can really explain retrograde motion only came with Copernicus, Galileo, and finally explained by Newton physically. So what happens, this video might be a little confusing, but basically this is the point of view of the sun. This is the sun point of view, right? You have two planets go around the sun. The sun is constant, it doesn't move. And then Mars and the Earth are moving around the sun. Mars is the outer planet, the Earth is the inner planet. The Earth has a period of 365 years. Mars is about twice of that. But if you go to the Earth perspective, which we are on, right? We're on Earth, so we're on Earth perspective. The Earth is now constant. If you ignore the rest of the things that are moving, the Earth is not moving. Everything else is rotating around the Earth, right? And if you do that, plus the Copernican model of the sun, then you see that everything starts to make sense. Why does it make sense? It makes sense for this loop to happen because right now, you see Mars, you see it right there. But Earth is closer to the sun than Mars, and Earth has a shorter period than Mars. So Earth actually moves faster than Mars. And right now, it's behind Mars. Eventually, it will catch up to Mars, and then it will be faster than Mars. And when that happens, you can just literally draw the line of what we might see from Earth to Mars, and you can actually just reproduce that motion. And it's easy to say right now, oh, obviously, why didn't people think about this? And it actually took a long time to actually understand. The ancient Greeks actually were able to make this prediction, but it involves a lot of little circles here and there, and they add on like 6 different circles, and it just gets really complicated. The amazing model by Copernicus et al. In the 16th century was that they were able to explain this in a very simple way. Just a sun in the middle, and everything just magically. All right, so what's next? What else is moving other than the planets? Well, this is moving. And this is not moving on the timescale of years. You might see the bottom here. It says sub-second. This thing moves on the time scale of seconds, right? At most seconds. Does anyone know what this is? Meteor, that's right. Also known as a shooting star. A lot of people like to call it with that name. But these things are really, really bright. So what these things are, so the Earth moves around in its orbit, and sometimes it encounters rocks in space. There are plenty of rocks in space, quite a few of them actually. And what happened is they enter the Earth's atmosphere. The Earth's atmosphere is pretty dense, and it flies in at a really fast velocity. And when that happens, it gets really hot. It gets ionized, which basically means its electrons are just strip away from the atom. So this thing is like a really, really weird plasma behavior kind of thing. You don't need to know what that means, just know that it's really bright. And it's really hot. And usually it's so hot that it evaporates in the atmosphere, it doesn't even reach the Earth. If it does reach the Earth, it's called a meteorite. If it's big enough and it reaches the Earth, we just die, so maybe that's kind of bad in that sense. There was one explosion in Russia in like the 2010s, so it does happen. So how do you spot these things? Well, this is kind of the same as the Milky Way one. You just find a relatively dark spot. Toronto would be a pretty bad place, but you drive an hour or two out. You can actually just sit down on some grass, look up for a few hours. If there's no meteor shower, which I will talk about later what those are. If there's no meteor shower, you probably see about like 5 a night if you're lucky. But it does happen every night. So you will spot one if you're just consistent. All right, does anyone see anything funny in this picture other than the clouds? Comet, right, it's that thing right there. It has a little weird shape. It has a little fanning thing out. So here's a better picture from people that actually are professional photographers. So some of these are comets that we have that have been visible in the sky. There's usually like 1 or 2 every like 5. I don't know, I just made that up, but that sounds about right. There's like 1 this year, there's 1 last year, so I guess something like that. And they're pretty bright sometimes. Sometimes they're not bright, but usually when they get really close to the Earth or the Sun, they can get really bright. And I'll talk more about that. And these things are not fast, right? People think this is a shooting star. It's not that. One day you look in the sky and you suddenly see something like that, and it gets brighter and brighter and brighter over the course of several weeks, several months. And then it gets dim, 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 and then it disappears. This is not a second kind of thing. This is like, oh, there's a comet. You can go look at it next week, tomorrow, kind of a thing. And you can usually read the newspaper. Sometimes they're good at that. Sometimes they're not. But basically what happened is comets that we can see are typically ones that have very eccentric orbit. So usually, so the Earth orbit is circular, right? It's a circle, approximately circular. And then the comets are much more eccentric. They can go from very far away from the sun to very close to the sun. And when they get really close to the sun, the comet can actually evaporate a lot of the ices that it's composed of. And when that happens, these ices reflect sunlight, and we can see it makes these tails. It's called the coma tail. They also release dust, which is actually quite important because I'll talk about dust later. So if you actually want to spot comets, I have to plug my advisor. My advisor likes to make Apple App Store apps. So he made this app. So if you have an Apple device, this might be helpful. Yeah, it's called Bright Comets. And for anyone who can't read too far away, if you enable location, it actually can like tell you where the comet is on the sky and how to find them. Yeah. So what actually are comets, and how do we? So before we can answer what are comets, we have to ask how do we study comets in the solar system. So a great example was this comet, comet Shoemaker-Levy 9. In 1994 or 1995, it crashed into Jupiter. And as it flew into Jupiter, it gets pulled apart. It's called tidal disruption. Fancy word for it literally just means Jupiter's gravity is pulling it so strong near it that it's getting torn apart. And this is actually really important because we can finally know how strong is a comet, right? Imagine if we want to know how strong is a plate is. The only short way to do it is trying to smash the plate. This, how strong the plate is how much force you need to smash it, right? Or what is the material strength of Play-Doh? How do you pull these Play-Doh thing apart? Well, you just have to pull it until it breaks, right? That's actually how engineers test anything, right? They test car crash like that, so yeah. Another way to study a comet is that we can land probes on them. So this is Comet 67P. I will not attempt to pronounce the latter half of that name. And the cool thing is we literally sent a probe and it landed on the comet, which allows us to collect materials and study them. And a cool fun fact, the P in the naming convention, the P just means periodic. So this comet is periodic. It means it will come back, it comes back in a period, right? There are aperiodic comets and there are comets that get disrupted, yada, yada, and they would have different numbering. But 67P just means it's the 67th periodic comet that we know. And then there's one that we purposely crashed into. And you're like, why would you crash into a comet? Well, landing a Lando probe on a comet is like trying to like see the surface level, right? You have like a mosquito trying to like bite you and it gets like the top level of the skin. Crashing into a comet is like bringing a sledgehammer into your bone, right? And that will tell you about the bone structure, right? And this will tell you about the internal structure of the comet. Sorry for the graphic description. But that's what it is, right? You have to crash into it to see what's deep below the level, right? And of course, the old traditional way that has been done for thousands of years is to just look at them from the Earth. And from the Earth, you can actually see quite a bit. You see there are two tails of comets, and the colors that they emit in, and that can actually tell you what's made out of these gases that's coming out of comets. So what did we learn about comets? Well, from the one that crashed into Jupiter, we know that they are weakly held together. They're what's called rubble piles. They are very weakly bound. Just imagine a pile of rubble, right? It's not gravitationally bound. These things are not big enough to have sufficient gravity to pull the material in strongly. And they're not as small like your phone. Your phone is bound by tensile strength. Go ask your favorite engineer what that means, but it basically means the material itself can bound itself. I forgot to mention they're usually small bodies, they're usually about 1 kilometer in size. That's about the typical size of most comets. They can go pretty high up. There are some comets in the tens of kilometers. So that's about like size of Toronto kind of ish. So in like one direction. And they are, from landing on a comet, we know, and I guess from that picture you can tell, it's made out of rocks, and also that picture. It's made out of rocks, like the rocks that we have on Earth, right? Not too much different from that. And it's made out of ices. Now this is where the fun part, I think, is. So these ices are, comets are made out of a composition of both rocks and ice. Ice does mean water ice, like the ice that you know we put in the fridge, but also ice of volatiles. Ice of things like methane, ammonia, things that you like, oh, how is that an ice? It's usually a gas, but it's an ice because it's so cold in space, right? And it becomes ice. And these ices are actually, we landed on them and we find that they are actually full of organic materials, which are very important for life. And you can see that these ices, they get evaporated as the comet gets closer to the sun. When it gets close to the sun, the comet heats up and the ice evaporate, right? Just like if you bring ice from your fridge into the oven, for example, and then it melts and it gets evaporated really fast. And it also leaves behind debris. So you see that there's a gas tail, dust tail, gas tail, dust tail. This dust tail is actually what explains a lot of these meteor shower that you might have heard about. There's a meteor shower recently, it's the Perseid. And you're like, why do we, like, every year in August we get a meteor shower? Why is that so periodic? Well, it turns out every year when the Earth goes around the sun, it encounters these clumps of rocks. And when that happens, the rocks get into the atmosphere and it makes a meteor shower. But the question is, where are these rocks coming from? For most of these, for a lot of these, we know a lot of these rocks are left behind from a comet. For some meteor showers, we can actually identify which comet caused which meteor shower. Because as the comet comes in, it leaves behind dust and debris, and that is actually what enters the atmosphere, and that's what gives you the Perseid and whatnot every year. And this is what you would see. It's actually not, you would not see that. That's a lie. That's an absolute lie. You will not see that when you go see a meteor shower. A lot of people think this is what you see. This is actually what you would see, which is still a lot. Remember, without a meteor shower, it's like 5 a night if you're lucky. This is like, that's 1. This is over 1 night. You can see that time has changed because the Milky Way moved, right? So that's 2, 3, 4, 5, 6. So this is about probably an hour, just based on how much it moves. So you see, like, 10, maybe 20 an hour if you go to a really, really dark sky. This guy is not in a very dark sky. Oh, that's a really good one. A lot of the colors you see is actually from what kind of materials is being evaporated and burned up. Different metals burn differently. This is not a safe experiment to advocate, but you can try go home and burn metals, and you will see that they burn differently. The pink purple thing is an aurora, which is not my domain because it's not really, it's in the Earth. I do astro, which is outside of the Earth, but also cool. Also something you can see at night sometimes. So that's meteor shower. So as I said, comets are really rich in frozen water. They're really rich in organic materials. And sometimes they pass close to Earth. You can imagine if the Earth is on the path of the comet, it can actually hit Earth. And that's actually really good. It's good for life on Earth early on. For the early Earth, some people believe that a lot of Earth's surface water was actually delivered by comets. As in, when the Earth was young, a lot of comets hit the Earth, and it creates, and it delivers all the water and organic materials, supposedly, for life on Earth. So it is potentially a very important, necessary ingredient, component to bring ingredients for life on Earth. And of course, it's also very bad for life on Earth because one hypothesis that could potentially cause the dinosaur mass extinction is a comet, or something the size of a comet crashing into the Earth. So now that we've talked about what are comets and how we learn about comets, where do they come from? So comets typically come from a place called the Kuiper belt, which is this belt of material between 30 to 55 AU. So what's an AU? So an AU is distance between the sun to the Earth. Now, why do astronomers use AU? AU just stands for astronomical unit, by the way. Not very creative name, but it's an intuitive way to think about large distances. Because I can tell you, the comet is about 10 to the 12 centimeter, and you're like, what are you talking about? And you're right, it is not intuitive, right? Like, the Earth is 1.5 times 10 to the 11 centimeter. Sure, but like, I don't know what that means. Could be meter too, sorry. But if you scale everything to the distance of the Earth, everything starts to scale a bit more. So 30 to 55 AU just means this thing is 30 to 55 times the distance of the Earth to the sun away from the sun. So this is really, really far away. For references, Neptune is about 30 AU. So this is much farther than all the giant planets that we have in the solar system. But we have sent a couple probes and landers through there, so it's not something that is unreachable. And they can also come from somewhere called the Oort cloud. You can tell from the name that it's no longer a belt, it's a cloud. So it's a sphere of comet. And the Oort cloud is 5,000 to 100,000 AU away. So this is way, 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 way further away than the Kuiper belt. The Kuiper belt is 30 to 55. This is 5,000, right? This is 100 times more, right? It's a lot further away. So the question is, well, actually, before we go to questions, The 100,000 AU part is actually quite important. The 100,000 AU is about approximately the boundary of the sun's gravitational edge with the galaxy. Objects that exceed this distance can be lost quite easily to the galaxy because we live in a galaxy. The galaxy itself has have a gravitational pull, right? The sun has a gravitational pull, but if the pull of the galaxy is greater than the sun, you just lose your objects to the galaxy. So this 100,000 AU is the boundary of the sun's gravitational influence. So how many comets are there in the Oort cloud? This supposed distant reservoir of material. So there's about 10 to the 11 objects in the Oort cloud, which is about the same as the number of stars in the Milky Way. That's a picture of the Milky Way that I showed earlier. And that's not even the full Milky Way, right? This is just like a small part of the Milky Way. So it's a lot of stars. And if that's not intuitive for you, this is about Mark Zuckerberg's net worth in US dollars. Actually, he's richer than that, so think about that. So now that I've talked about Oort clouds, which you just know that it's this cloud of materials super far away, what will happen to the Oort cloud comets, which is now we're going toward more of my research. Before we go into that, though, we have to talk about what will happen to the sun. So currently, this is a very bad diagram of the solar system, not to scale at all. But basically, you have the sun, you have Mercury, Venus, Earth, Mars. Unfortunately, in about 4.5 billion years, the sun will be something like that. And all the inner planets, except for Mars, the sun will probably expand its radius to about the distance of the Earth. And the Earth might or might not be swallowed, but Mercury and Venus will almost certainly will be. And after that, the outer layer of gas just kind of puff away. There are no supernova, no explosion. It's just kind of gently puff away. And it leaves behind this thing called the white dwarf, which is a stellar remnant. So a white dwarf is just the core of a star after it's something called main sequence evolution. It's done, basically. It will stay like this for a long time. There's no fusion, so typically stars are supported by fusion. Just know that without fusion, a star will collapse, but this object is so dense and it's supported by a weird quantum mechanical effects that I will not even try to say, or you can look it up if you want. It's called electron degeneracy pressure, but you might need like a physics degree or something to understand that. But just know that there's no more fusion. It's kind of boring. There's not much really going on. There's a lot of things going on, actually. I shouldn't say that, but there's a lot of people who do research on white dwarfs. I don't want to disparage them. But there's no more fusion. It's quite small. It's about the size of the Earth. The sun right now is about 100 times the size of the Earth. This is about the size of the Earth, so it's about 100 times smaller. It's very, very dense, as I mentioned. The atmosphere, there's a slight, very small layer of gas around the white dwarf that we call its atmosphere, and it's just made up of hydrogen and helium. This is the final fate of the sun. And I say it's made out of hydrogen and helium, at least it should be. But on about 25 to 50% of white dwarfs that we see something called metal pollution. So what is metal pollution? It's not the same as pollution that we see on Earth, like that. So it's not too far apart, actually. It's literally, we see elements that are heavier than hydrogen and helium, and it should not be there. And the very easy answer why is, you imagine you drop a piece of metal or plastic or anything in water, it will sink because it's heavier than water. The same thing happened here, except it's hydrogen and helium, to which hydrogen and helium is even lighter than water, right? So everything should sink down. And in fact, everything should sink down so fast that we should not see it on old white dwarfs, but we see it on white dwarfs across all ages, up to white dwarfs with 8 billion years old. And that is way too old to see consistent white dwarfs, pollution on all white dwarfs. So one answer is actually the answer is something must be hitting the white dwarf over a very, very, very long time, very constantly. And how much metals is actually hitting the white dwarf? I like to work in intuitive units. So it's 1 to 10,000 adult elephants is hitting a white dwarf per second. So that's actually a lot of material in white dwarf. And if you, I don't want to be memed on by not working in normal people units. So this is 10 to the 6 to 10 to the 10 grams per second. I'm not sure how much intuition you might gain from that. But I do know that 10,000 adult elephant is approximately 1 seed. So that might be a bit more interesting. Per second. So it's a lot of materials. And of course, no elephants or CN towers were born in this research. So what will happen to these, back to, now we know that the sun will become a white dwarf. And now we know that there are comets, the Oort cloud that will be around white dwarfs, hopefully. Let's assume that there's an Oort cloud around white dwarf. What will happen to its comet? Well, there's this thing called the galaxy, which lived in the background, right? As I mentioned earlier, the galaxy also has a gravitational field. And again, these comets live so far away that it's actually pretty comparable forces between the gravity of the galaxy in the background and the gravity of the white dwarf. When that happened, something like this could happen. The orbit of the comet can become a lot more eccentric. It gets pulled out. You can roughly kind of intuitively think why it's pulled out, right? Like it gets pulled by the galaxy out. And when that happened, the orbit becomes more eccentric, and then, oh, it hit the white dwarf, right? So my thesis, not my thesis, I guess part of my thesis asks the question, if you can deliver something like Oort cloud comets into white dwarf and be that a source of material. And it turns out you can. If you assume that there's a Oort cloud like this one that we have around the sun exists around most stars, there's no reason why we should not expect that. So it's actually a pretty plausible hypothesis that an Oort cloud can actually be delivering materials. And so I run simulations, lots of calculations, and I showed recently that you can actually deliver materials comparable to what you would expect for white dwarf evolution. So my research involves a lot of calculations and simulations. That's why I'm not going to talk about it. But if you're really insistent, I guess you can find it or talk to me after. An easier read, though, someone made a more popular summary of my research on BBC Sky at Night. So if that's something you want to read more about, you can read about it. But I mean, they just summarized exactly what I just said. So before we finish, I want to give you a gift of one more thing that might happen on the sky at night. That's an aurora. I took this picture 1 hour away from here. So you can do it from here. You just have to be really lucky. So good luck. And finally, there's this quote by Newton from the year 1704. And the quote is, while comets move in very eccentric orbits in all manners of position, and then he goes on this weird diatribe about things. But you can see that this problem has been going on around for hundreds, thousands of years, right? We worry about how things move, and there's a connection. And then these all techniques of what comets are, how they move, they actually can answer modern research problems. So this is a very rich field of study. It's a very old field of study. I enjoy working on it. So if you have any questions, I am more than happy to answer them. Oh, and I hope you can understand what's in the back. Thank you.
Thank you so much, Pham, for that wonderful talk. We're going to take some questions now. I'm just going to leave the lights on a little bit. Does anyone have any questions for Dan? Yeah, right there.
Yeah, the question is how do the dust gather together after they are ejected from the comet to make big clumps of rocks so that we can see them in meteor shower? The answer is, well, sometimes the dust just emit in big chunks. The dust actually comes in big chunks, not in like tiny little dust like you see, but like when I say dust, I mean like rocks, right? Like these are rocks. Not too big, but like, rocks. So they don't regather.
You mentioned that comets that we see from the random detector grounds or you already shot. I was just wondering if there's some sort of proportion to how many comets you see from the Kuiper belt in relation to, or in proportion to
And the question is, how many comets come from the Kuiper belt versus how many comets come from the Oort cloud? The answer might have to refer to Mark, because we don't really have much of a. The Kuiper belt, both the Kuiper belt and Oort cloud are still pretty much areas of research, and it's actually really hard to detect comets in general. They are really dim when they are far away. So we actually don't know how many comets are in the Kuiper belt. We actually don't know exactly how many comets are in the Oort cloud either. So the answer is actually we don't know. Sorry.
I could say something else.
Yeah, make some.
Yeah, in the back up there.
Yeah. Sorry, I can't hear.
Why are rubble piles held together?
Why are rubble piles held together? They aren't really. They just kind of like snap together and kind of like stick. It's held a little bit by gravity. It's held a little bit by tensile strength, just the thing I talked about earlier. It's just it's not really held together that well, which is why it's also really easy to break comets apart.
Yeah, a little closer.
Where does the organic materials come from? That's also a research level question. We see organic materials in the interstellar medium, which is just gas floating in space between stars. We see them in many places across the universe. So I mean, they just form. Somehow they form. It's cold out there, so they're pretty stable. They don't get evaporated and broken apart. But where do they come from originally? We don't know.
Dan, could you clarify what you mean by organic materials? Are there little aliens on these comets?
No. Well, find your favorite chemist, but they have a very specific definition of organic and inorganic. But organic, just think of things like things that we produce, or like plants and animals, like methane, ammonium. Not water. Water is not organic.
Standing up there.
What gives comets elliptical orbits? A lot of times, comets can interact with planets, right? We have a bunch of planets in our solar system. For example, when a planet goes close to Jupiter, for example, it can get a kick by Jupiter, and that can make it go eccentric. As I mentioned, the galactic tide, the galaxy itself can also make something eccentric at long distance, further distance away. But that's usually the main mechanism. There are some other mechanisms, but that's a lot. Yeah.
Over here on the stairs.
How many of these Oort clouds were around this?
How many? How common are Oort clouds around other stars?
How common are Oort clouds around other stars? The answer, the good answer is we don't know. That's what a good scientist would say. I would say that it should be natural to expect them. So the Oort cloud forms because in the early solar system, planets move around, and as I said, when a planet moves around, it can interact with these small bodies like comets, and you can actually eject the comets, right? You kick the comet, it goes into this long distance away. So, that should happen in every planet, in every planetary system. Most planetary systems have a planet, right? So they should also kick their comets out, and they should also form Oort clouds. So they should be common.
We'll go right there in the middle. Yep.
why would the gravitational influence change when it becomes a white dwarf? With all the mass still be the same?
Why would the gravitational influence change when the star becomes a white dwarf? So it does change because the sun does lose about half its mass. So the sun does lose, a decent amount, but it's still like 0.5 sun mass, so it's still a pretty big, gravitational influence. So the answer is we actually do see comets get influenced by the galaxy, and they do come in because of galactic tide. And we do see Oort cloud comets come from 10,000 AUs away, and they come in here because of that exact mechanism.
And we'll go right there.
The question is my paper saying all pollution are due to comets? No, I will never claim that. In fact, there are many issues with using comets, with explaining Oort cloud pollution by comets. The biggest issue is that we don't see organic materials on white dwarfs. As I mentioned, comets are full of organic materials, but if they're comets, why don't we see organic materials on them? There are more answers on why we don't see that, but you should talk to me afterward. But I think the right answer is, I think some systems are polluted by Oort-cloud comets, and some systems are not dominated by that.
I think we have time for one more, and by the wall in the third row there. Yep, it is.
You said astronomical units are distance from Earth to the sky. Is it the Earth in an elliptical orbit? So is it shortest, longest?
So the question is, how is astronomical unit defined? Because the Earth is in a slightly elliptical orbit. Yes, the Earth is in a slightly, very, 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 very slightly elliptical orbit. It's basically circular for all intents and purposes. So for elliptical orbit, you can define something called a semi-major axis. You're welcome to open your grade 9 geometry book to know what that means. But basically, it's just one of the distance. But because it's really not that eccentric, it actually doesn't matter. You can just measure the distance of the Earth at any point. It's roughly the same.
Okay. Thank you for all those great questions. I'll take that one more time.